Say you run a small clinic and you want an AI that answers patient messages in your exact careful style, never guessing, always gentle. Or you teach, and you want one that explains things the way you do. You want to make a giant model yours, and the natural assumption is that this is a job for a giant lab, that you would have to retrain the whole thing from scratch, all those billions of numbers, on rooms full of expensive chips for weeks. That customizing an AI must cost a fortune and is simply out of reach for a normal person. That assumption used to feel true, and it is wrong, and the reason it is wrong is one of the most elegant tricks in modern AI. You do not move the mountain. You bolt a tiny patch onto it. Today, how you make a model yours on hardware you could rent for the price of lunch. Before you change anything, you have to ask the right question because most people ask the wrong one. There are two completely different things you might want to change, and confusing them wastes everything. One is what the model knows. Your prices, your documents, today's news, facts it was never trained on. The other is how the model acts. Its tone, its format, a skill, the shape of its answers. And here is the key. These are not a ladder where you climb from one to the next. They are two separate dials. If you only needed to know your facts, you do not fine-tune at all. You hand it the facts at question time. That is retrieval, often called RAG, retrieval augmented generation, the exact system you built back in Season 2, looking things up in your documents and pasting them into the prompt. Fine-tuning is the other dial for changing behavior, and the beautiful part is they stack. You can fine-tune a model to act like your assistant and still let it look up your latest documents. Know versus act. Retrieve versus fine-tune. There is even a heavier third option, continued pre-training, where you keep training the base on a whole new field's worth of text to soak up its jargon, the way a chip company did to teach a model its hardware language. But for almost everything you will want, it comes down to those two dials. Get that split right, and the rest is easy. So you want to change behavior. How do you actually teach a finished model a new habit? You show it examples of the habit you want. This is called supervised fine-tuning, SFT, and the recipe is simple. You write out pairs. Here is a message a patient might send, and here is exactly how I want you to reply. Dozens of these, then hundreds. Then you let the model practice predicting your ideal reply and nudge its numbers whenever it drifts. One subtle but important detail. You only grade it on the reply, not on the patient's message. In the jargon, the loss is computed on the response tokens only. The model is not supposed to learn to write the question, only to answer it the way you would. Now, how many examples does this take? Less than you would think. A well-known study found that on the order of 1,000 carefully chosen, high-quality examples were enough to set a model's whole assistant style. Quality crushes quantity because nearly all the knowledge is already in there from pre-training. You are not pouring in a new brain, you are teaching the one you have some manners. But one honest warning. If you fine-tune the model to confidently state facts it never actually learned, you are not teaching it those facts. You are teaching it to sound confident while making things up. Behavior this teaches beautifully. New facts are a different problem. Now we hit the real obstacle and the real magic. A big model's knowledge lives in enormous grids of numbers, its weight matrices, millions of values each. Normal fine-tuning means nudging all of them at once, which needs the memory and the muscle of serious server hardware. Here is the insight that broke it open. When you adapt a model to one narrow task, the change you actually need to make turns out to be small and simple. It has, in a precise mathematical sense, a low rank. So you do not touch the original grid at all. You freeze it completely. Then beside it you place the change you want, but you forbid that change from being a big dense grid. You force it to be the product of two thin strips, call them B and A, a tall, narrow one and a short, wide one. The skinny waist where they meet is the rank, and you choose it, often just 8 or 16. Multiply those two strips together and they reinflate into a full-size update, but because they squeeze through that tiny waist, they can only ever hold a sliver of the numbers. One neat detail, You start the B strip at all zeros, so on the very first step the patch adds nothing and the model behaves exactly like the untouched original, and learning grows from there. Watch the count. A full grid might have you training hundreds of millions of values. The 2 strips, just a few 100,000. For the original giant model this was first tried on, that worked out to roughly 10,000 times fewer numbers to train, an adapter small enough to email. This is LoRA, low-rank adaptation, and the final touch is the cleverest part. When you are done, you multiply the 2 strips out and add the result straight back into the frozen grid. It melts in, and you are left with one ordinary grid again. So at the moment you actually use the model, it runs at exactly full speed. The patch costs you nothing at runtime. Leave it unmerged and you pay a little extra compute per step. Merge it and that cost disappears. But there is still one problem, and it is about your hardware. Even if the patch you are training is tiny, the frozen base model still has to sit in memory the whole time you train. And a really big model, tens of billions of numbers, simply will not fit in a single affordable graphics card. So someone asked the obvious question. The base is frozen. We are never changing it. So why store it at full precision? And they squeezed it. Each weight in the frozen base, normally kept in 16 bits, gets crushed down to just 4. The clever part is how. A trained model's weights cluster in a bell curve around 0, so they pack the 4-bit values densely where the weights actually live, a scheme called NF4. The common weights land almost perfectly, and barely any information is lost where it matters. The tiny trainable patch stays sharp and full precision, but the giant frozen base shrinks roughly 4-fold. The result was striking. A 65 billion parameter model, which had needed a rack of server GPUs to fine-tune, now fit on one single graphics card you could rent for a few dollars an hour. This is QLoRA, the Q for quantized. And almost overnight, fine-tuning a serious model stopped being something only a big lab could do, and became something a determined hobbyist could run overnight on rented or even home hardware. The whole family of tricks here, freezing the base and training only a tiny add-on, has a name you will run into everywhere. It is called parameter-efficient fine-tuning, or PEFT. LoRA and QLoRA are its 2 most famous members. Now step back and notice what we have actually built, because this is where it gets wonderful. The expensive part, that giant base model, is frozen and shared. The thing that makes a model yours is just a tiny patch, a few megabytes, small enough to attach to an email. So what happens when 100 different people each train their own patch? You do not need 100 giant models. You keep one single frozen base in memory, and you snap different patches onto it on demand. One moment it is wearing your clinic's patch, writing gentle patient replies. The next, someone else's, and it is a legal assistant. The next, a coding tutor. Same enormous brain underneath, swappable personalities clipped on top, like a single game console with a stack of cartridges. Serving systems built exactly for this can hold one base and juggle on the order of a couple thousand of these adapters at once. So the real shift LoRA caused is not just cheaper training. It is a different shape entirely. One shared mind, and a whole library of tiny patches that each make it someone's own. Before we close, 2 honest corrections, because the internet oversimplifies both. First, you will hear that fine-tuning simply cannot teach a model new facts, that for facts you must always use retrieval. That is too strong. What one careful study actually showed is narrower. For stuffing raw new facts into a model, one particular flavor of fine-tuning, the kind that just keeps reading documents with no question-and-answer examples, lost to retrieval. That is a real and useful finding, but it is not a law that fine-tuning can never carry knowledge. The clean rule still holds. If it is fast-changing facts, reach for retrieval first. If it is durable behavior, fine-tune. Second, the tiny patch is not always free. On the hardest brand-new skills, like learning to write code or do heavy math from scratch, a small low-rank patch can genuinely learn less than full retraining would, though in exchange it forgets less of what the base already knew. For most real customization, matching a tone, a format, a narrow domain, the tiny patch is more than enough and the trade is overwhelmingly worth it. But it is a trade, not a free lunch, and a good engineer knows which is which. And the patch itself keeps getting smarter. Newer refinements split it into a size and a direction to capture even more, so this is a live, improving idea, not a finished one. So making a model yours never meant moving the mountain. First, you ask the right question. Do I need it to know something, in which case let it look things up, the retrieval you already built? Or do I need it to act a certain way, in which case you fine-tune? To fine-tune behavior, you show it about 1,000 carefully chosen examples and grade it only on the answer. To do that without a data center, you freeze the giant model and train a tiny low-rank patch beside it, thousands of times fewer numbers, that melts back in for free at runtime. To fit the frozen base on one affordable card, you squeeze it to 4 bits. And because each patch is so small, one shared brain can wear thousands of them, a different personality for everyone. A giant model is not a monument you can only admire from a distance. It is a foundation. And anyone with 1,000 good examples and one rented GPU can build their own room on top of it. Next time, once you have shaped how a model behaves, we ask the harder question. How do you teach it not just to copy good answers, but to prefer the better one to reason, and to know when it is wrong?